Hi, Professor. I picked a concrete compressive strength problem. This photo is actually the company that my father-in-law worked at for 30 years in Germany. The data came from the UC Irvine Machine Learning Repository. It's a regression problem. Basically, cement and water make a paste that binds sand and gravel, fine aggregate, and coarse aggregate, respectively, into concrete. The slag, fly ash, and plasticizer or additives that change the properties of the concrete. Age is measured in days. The first 28 days is the initial hydration period where molecules in the cement harden. And there's a secondary hydration process that starts from day 1 to day roughly the year mark, where additional hardening happens from slag and fly ash if it's present in the mixture. MPa is our target variable. That's the compressive strength of the concrete, the amount of compressive force that was applied to the concrete before it broke. We're able to see some of the interactions in our predictors that we learned in the domain dive play out in the correlation matrix. So the more cement there is, the higher the strength of the concrete. The more age, the higher the strength of the concrete. The more water, the lower the strength of the concrete. That's because the more water you have, the more porous the resulting concrete is going to be, which weakens it. The biggest negative correlation is between superplasticizer and water, and that's because in order to get these high cement, low water, really strong concretes, you still need it to be workable. And so adding the superplasticizer allows it to be poured, allows it to be shaped into its final shape without needing so much water and resulting in really high concrete strength. We knew that this wasn't a nonlinear, or this wasn't a linear model and or a phenomenon, and we still wanted to run the linear regression model to see what we could learn. We found that coarse aggregate and fine aggregate, the gravel and sand, don't have on a linear basis any impact on the prediction of hardness. We found that the residuals were normally distributed and we didn't need to do any transformation of our data. We found in experimentation that if we took gravel divided by sand, the coarse aggregate divided by the fine aggregate, then that was predictive. However, in our subsequent nonlinear models, we don't need to pull that out as an interaction term. That interaction will be found through the nonlinear models. Random forest gave us 92% accuracy, helping confirm that this really is a nonlinear process. And in fact, when we did the grid tune for mTri, the number of predictors used to make each tree in the random forest, the ideal number was 4. And presumably one of them is age. That means 3 of the ingredients are coming together to come up with help inform how hard the concrete is going to be. We looked at support vector machines. It caused so much consternation in the last assignment that was category heavy. Here, it implemented very smoothly. It didn't have as much predictive power as random forest, 89% R squared. However, we did have this beautiful partial dependence plot. So we're looking at water and cement, and we're able to see how they interact related to hardness. And we're seeing that the hardest concrete is when it's really high cement and really low water. If we were to look at a third variable, I would pick plasticizer because we would assume that in order to get that really low water to cement ratio, we would need a lot of plasticizer. XGBoost was our winner model. It had an R squared of 94%. And it also, we able to generate partial dependence plots. The hypothesis and what we see here is that if there's really high slag, which takes roughly a year to fully harden, that we're not going to see the strongest concrete until we're getting close to that 1 year mark. And that's that yellow in the top corner. The clustering worked out really well. Our our thought process was all of these mixtures could be grouped into recipes for specific applications. And the first one we identified was number 3. It's architectural concrete. It's identified because it has a really high component of slag, and that makes it lighter in color, a smoother surface, and so it looks really beautiful in modern homes with lots of glass and concrete. Number 2 is Portland concrete. That's your run-of-the-mill sidewalk concrete. It doesn't have expensive slag, ash, or plasticizer. It's got the highest cement amount. Number 1 is fly ash concrete, identified because it has high fly ash. This is used in large infrastructure projects like dams. And it's interesting, the cement reaction that hardens into concrete, not only it releases heat, and so fly ash, which has a much longer time to do the same reaction, slows down that rate of heat. And if you have a really large infrastructure project, that heat from the cement hardening can create a temperature differential that would actually crack the dam. And so they add fly ash to lower that rate of reaction, lower the amount of heat being produced, and then it has more time to hydrate and harden and without cracking the dam. Professor, thank you so much. It was a great class, and I really enjoyed working on this last problem and feeling good going into the next semester. Thank you. Take care. See you in the fall.